this series of short videos, we'll be examining the concept of resonance. Resonance is a key concept in understanding organic chemistry. However, it often gives grief to organic chemistry students. Therefore, it's important that we delve into some of the key ideas. To begin with, it's helpful to think of resonance as a patch-up concept. Here I show a representation of a carbocation organic compound, and we use the bond line representation. Bond line drawings and Lewis structures are incredibly powerful and helpful in representing structures. However, they do have a limitation in that they may not completely represent what's going on with the structure. So for instance, if you look at the bond line representation on the left-hand side, it shows the positive charge on the rightmost carbon. We understand that actually the positive charge coexists on both outer edge carbons, on the rightmost carbon and on the leftmost carbon. We understand this because the actual structure is a fusion in the sense of two resonance forms. We can use curved arrows to help us explore or find, if you will, a second or a third resonance form. So by understanding that the pi bond exists between the rightmost two carbons and the leftmost two carbons, we understand that the actual structure is a fusion of these two. In a sense, we could say that there are 1.5 bonds between each of the carbons, and there's half a positive charge on the outermost carbons. As you're looking to draw resonance structures, it's helpful to keep a number of key points in mind, or if you will, some rules. So one of the key rules here is avoid breaking a single bond or a sigma bond. Resonance forms will always, to some degree, involve pi electrons. So for instance, the following can happen, if you will, but it's actually the result of a chemical reaction. So single bonds can be broken, and in this case, this is what would happen here. The single bond between this carbon and this carbon would be broken, and we would result in forming a carbocation right here. But this is a chemical reaction. We're not finding a second resonance form. Another thing to keep in mind in looking for other resonance forms is never to exceed an octet for second row elements. And so in particular, we're talking about carbon, nitrogen, oxygen, and fluorine. These elements will always have at most 8 electrons surrounding them in a chemical bonded structure. They could have fewer than 8 electrons, and we'll look at some examples a bit later, but they can never have more. So for instance, the leftmost anionic structure, if we're looking to find a resonance form, it would not be possible to find a resonance form such as I'm using the curved arrow here, because it would therefore bring too many bonds to that central carbon, or too many electrons to that central carbon. So there is no resonance form associated with that, nor are there resonance forms associated with my showing of the curved arrows with these other two. However, we can find a resonance form by doing the following. And so that implies that the pi electrons move up to the top oxygen. Now I say move. In fact, there's nothing moving here. It's just looking for a more complete representation of a single entity. So the actual structure for this ketone is a fusion of both of these resonance forms. One of the things to take note is that I haven't drawn in the lone pairs on the top oxygen. I hope you understand that there are 3 lone pairs, and as such the oxygen has a negative formal charge. The carbon has a positive formal charge. It is making 3 sigma bonds, and there are no other lone pairs of electrons associated with that central carbon. One of the things that you may also notice is that carbocation right here is indeed actually breaking the octet rule. But in this case, it's breaking the octet rule by having too few electrons. So this guy has too few electrons, and that definitely happens. It can happen for nitrogen and other elements, but we actually see it fairly frequently for carbon. Although when it does occur with carbon, usually we're looking for to what degree is that carbocation stabilized. Let's turn the page and look at the next example. Here we have a neutral structure, and we can look for a second resonance form by using the curved arrows. We can understand a pair of electrons coming down here to form a new pi bond, and then this other pi bond in a sense, moving its electrons to the other carbon. The second resonance form would look like this. Notice that there's a conservation of charge. The structure on the left is neutral. The structure on the right overall is neutral. Now at first, if you're a little rusty on your formal charges, it's helpful to write in the lone pairs. And I'm also going to write in the hydrogen, which is implied, and write in a lone pair here. If you account for the formal charge rules, you'll see that indeed the oxygen has too few electrons, and our carbanion has one extra electron, and therefore the resultant charges or formal charges on these atoms. The other thing to keep in mind is that these two resonance forms are not equivalent. One resonance form contributes more to the overall structure than the other. So to some degree, there is a positiveness to the oxygen and a negativeness to that carbon that has the negative formal charge on the right-hand side. However, the resonance form that contributes the most is actually the neutral resonance form. Now, there's a little bit of space in your booklet, and you might want to jot down some of these points so that you can distinguish and compare different resonance forms and decide which one contributes the most. So resonance forms that contribute the most are those which have more atoms with octets, those structures that have fewer formal charges, and if there are formal charges, it's better to have a negative formal charge on a more electronegative atom. It's better to have a positive charge on a less electronegative atom. And finally, if you are going to have formal charges, it is better for opposite charges to be somewhat close and like charges to be further away. Also consider that this list is hierarchical. So the most important thing is to have more atoms with octets and then indeed start to look at formal charges. Now it should be actually fairly obvious in comparing these two resonance forms that the resonance form that contributes the most is the one on the left. We can decide this not because we're looking at the difference in octets, because in fact all the atoms have an octet, but the resonance form on the right has more formal charge. And in fact, it's not that favorable in that the oxygen, which is fairly high in electronegativity, has a positive charge, and the carbon, which is fairly low in electronegativity, has a negative charge. Now, if we come back to these two bottom resonance forms, we can make a comparison and we can see that the neutral ketone on the left is the one that's favorable. And it's favorable for two reasons. One, it has no formal charges, but more importantly, all the atoms have an octet. Whereas the resonance form on the right does have formal charges, but also the carbon does not have an octet. Now, even if a resonance form does not contribute as much, it's still important to consider that it contributes somewhat because it will influence the overall reactivity of our compound. So coming back to this slide, in the next video, we'll start to look for those indicator signs for when you can expect to have a resonance form.